All right, so there we go. A couple things before we kind of dive into it here today. That's I think for one, I need to have this pulled up real quick. So there we go. So I put up on Canvas today is kind of practice questions. So sometimes I have these like in-class quiz questions that I think would be worthwhile kind of reviewing in class. They're also just good to kind of go back and review as we get closer to that exam. So I've got that in there. We'll take a look at that here today. What you'll also notice, I put up that third problem set last night. So I tried to adjust this based off of what we've covered. So the due date isn't going to be, until Tuesday, October 14th. Okay, so you'll have a good amount of kind of week and a half to work on this. And I've got two different problem sets we'll use. Now, some of the questions towards the end. So we're thinking about things like, joint significance. We likely won't get there today. Right. So I'm expecting joint significance we'll talk about on Tuesday's class. So you can still get through the vast majority of this problem set already. But if there's something that looks like we haven't talked about in class after today, likely the only real thing should be kind of talking about joint significance down here in these last couple questions. We won't cover that until Tuesday. So you should still be able to get through everything except for these like last kind of just part, what is it? C, and I think part of question 11, but everything else you should be able to start working on and kind of answer for problem set 3. Now we talked about a lot of the theoretical side of it, and I kind of showed you some of the output last class. We'll look a lot more at Stata today. We're kind of doing a lot of work in Stata, so that today's class will be kind of very helpful. A lot of the kind of later parts of this assignment, some of the earlier stuff, probably basic. I usually probably figure out how to do this on your own based off of what we've covered up to this point. So it's due that Tuesday. We have our in-class exam. So if we go to the files tab here, I kind of try to put all these dates that are important at the end. So our first midterm is going to be that 16th. Okay. So next week, you'll notice like even the topic I have here, kind of progression with a dependent variable, that includes some of the stuff that we've already talked about. So next week, I'm guessing that we're only going to see new on Tuesday. Next Thursday, I'll probably work through some more examples on Stata just to kind of help you out with that third problem set and also just to get more examples of what we've been talking about. But a lot of next Thursday's class and then that 14th, that Tuesday of the exam week will be primarily review. Okay, so what that's going to look like is I've also put up this folder, but I now have it published on the main page where I'm going to give you that formula sheet that I will give you on the exam. Okay, so we are going to have a formula sheet. Everyone will have the exact same one. You're not creating your own. So we'll probably talk through a lot of these things, what exactly they mean as we kind of review that next Thursday and Tuesday's class. Now you're also going to see a practice exam up there on Canvas. And I'll just pull up in the answer key just to have it all. So I've got kind of what this exam could look like. And I put up a set of like multiple choice questions. Right? But then notice there's also questions that are kind of fill in the blank. So the exam is going to be a combination of the two, right? And you'll notice sometimes it's just general questions. Other times you've got Stata output that you might need to use some of the statistics from, interpreting coefficients. When we get down here, right? Maybe this one is like using some of the different components. This is similar to something on problem set 2, where I might leave some things out or you might not have some information, but based off the statistics that you have, you can grab things and make a back of the envelope, so to speak, calculation to answer that question. Now, every question is a little bit different, but this is kind of what the exam will look like, right? A mixture of these things, okay? So we'll get a lot of practice with it. Like I said, if you have questions on this practice exam, next Thursday's class, we'll likely have some time where you can ask those. For sure, that Tuesday before the exam, I should see every seat in this classroom full, right? I wrote the exam, and so I probably know how to best use that time to be most effective for you, right? That means like I'm going to give you answers. I'm going to give you problems that look probably pretty similar to what you're going to see on the exam, okay? So those class periods are going to be really important, those 2 class periods before the exam if you're thinking about trying to study and do well for that, okay? Other than that, before we jump into material, I am going to go back a little bit today and use, where's that? This regression in class F25. We're also going to use the more recent one, kind of do file, when we're doing a lot of this work in Stata. So I might kind of go back to that if you want to have that do file open up as well as the current weeks. I also, that last in-class quiz, I had you all write your name down. So if you were here, basically got full points, right? We went through the exam answers together. If you weren't here, you got a 0 for that quiz. Okay? So I said these in-class quizzes are meant to be done in class. I can tell that, I mean, almost half of the class is not here, right? This worries me because then I'm going to get a lot of people upset with their midterm exam grade. Right? Also, I'm now probably going to have to start doing something I didn't want to do, which is creating a way on these in-class quizzes that I can almost guarantee that you're in class, right? So if you're trying to do these while you're not here, it is now going to become almost impossible for you. I won't tell you how I'm going to do that because that would spoil it, right? But next week, we will have another in-class quiz. And so these are meant to be done in class. I now have a way that I'm going to add to these quizzes to almost guarantee 99.9% that you're going to be here, okay? Without passing a paper, having you write down your name, because that's a little bit cumbersome, right? That is one solution I can do, though, right? So any questions? We've got that problem set 2, which I extended the due date because of that issue with Stata. Lost a day, so I'm already missing. Where is this at? Right here, right? We do at the end of the day tomorrow, okay? I'd like to see more of you kind of working on these early and coming into my office hours and asking questions. I haven't gotten a lot of that, but I want you to get as many points possible on these. They're only going to get more difficult. So that first one was pretty easy, right? They're going to get more and more difficult, and they're graded for correctness. So please, if you have questions on them, stop by my office to try to kind of get help with that. All right, that's my little spiel here before we get going. I'm gonna move this because I don't think we need to see that. Any questions before we jump into where we left off, which was talking about kind of making predictions using kind of a multiple linear regression? All good with everything? Okay. So we actually didn't go through multiple or imperfect multilinearity, but we kind of stopped at this traffic stop example. So I kind of had an additional omitted variable example that we're going to kind of start to work through. Also thinking about different types of multiple dummy variables. So we're going to start out here in Stata. Wish I can't have 2 screens, but it's easier probably to do this. So we've got this multiple linear regression week 6. Excuse me. One thing we haven't used up to this point is I've been giving you data sets and then you can open them. There's actually a whole bunch of free data sets that like exist in Stata that you can actually use, right? So I've got kind of this little preamble here. In order to do that, you have to install something to Stata. I believe this should work even though you're operating on it through IU Anywhere. If anyone's working along with me, you can tell me if it gives you an error here. Well, actually, I'm working on it as well, so it's not going to give you an error, right? So it basically uploads all these free data sets that we can now use. So if I had any data open, I'm just going to put clear. That clears everything out. I was actually opening some files before class just to kind of get my file paths to make sure they were right. So I'm going to have to clear this out. If I didn't, I try to open a data set. Well, I must have accidentally closed out the old one because it opened it up. So let's see here. I'll open up one. Let's just open up the COVID County data. I try to just, I guess the automatically clears this out. But if kind of fail safe, I always put clear in there. I think some of the older versions of Stata, maybe it wouldn't do that. Okay? So I've got this wage data set opened up, and you can kind of see now I've got all these variables: wage, hours worked, IQ, education, etc. Right? So when we were running these regressions with just a simple dummy variable, and I was trying to predict wage using IQ, and I said I could have like racial identifiers. We said, what did that dummy variable essentially do? So I'm still picking up the relationship between IQ, wages, but these dummy variables would change what if I'm thinking about lines of best fit. So it's just a 1-0 variable. We said it would change that line of best fits. If I think about any individual who is identified as white, non-black, I guess here, be what? Just the constant, whether IQ is 0. individuals identified as Black, their starting kind of wage would be the constant plus the coefficient on Black. So it's changing that intercept for these groups of where their line of best fit would start. Right. So I drew it last class. I had like, if we had two scatter plots, right, for these two different groups, whatever the dummy variable was identifying the groups as, it's essentially creating two lines of best fit, but changing that intercept. So this is kind of the use of our dummy variables. They look no different than any other variable. It's just when we look at the actual data, right, I've got just zeros and ones. Okay. So here's kind of something we talked about last class, where we're going to look at an omitted variable example. So I've got a bunch of different kind of comments in here, but let's kind of open up this GPA2, uploads that data set. I'm now going to regress kind of, or try to predict college GPAs based off of if this was a student athlete or not. So I kind of showed you this example last class, but where did it come from? So if I run this naive regression, that was kind of giving me, okay, it looks like being a student athlete has a really negative impact on college GPAs. But we said there's going to be a bias built in there, and the bias. So said if we just run simple linear regression, the coefficient estimate we see will be the true coefficient value, but plus, what did we call this? The bias. Right? So when I was kind of just trying to predict GPA, simply using whether or not they were an athlete, I was leaving off this important omitted variable, which was, I think it was SAT score. We'll see if that's the example I went with. Some measure of their kind of incoming ability, right? Coming into college. So we said that bias would always be whatever the effect of that variable would have been if I didn't omit it from the regression times was up here. Do we remember? So the reason why the bias was created is because the variable we left out was correlated with our Y variable, but also correlated with the variable we included. So in our numerator, we had, or sorry, this was going to capture the relationship between our Y variable and that omitted variable. Here, we want to capture the relationship between the independent X variable and that omitted variable. And then we said what's down here was the variance of whatever variable we had included. So we can actually prove this to ourselves in Stata that this is the actual bias, right? We can do it really two different ways, okay? So if I run the naive regression, this is my coefficient that has the built-in bias, right? If I were to simply include SAT, very simple way to identify that bias is, well, once I include the variable, I've gotten rid of that bias, right? So what was the bias here between not including SAT and including it? We went from negative 0.28 to negative 0.05. So the bias was what? About, gotta be able to subtract two numbers. So if the coefficient's negative 0.28, I then include the variable and it's negative 0.05, that difference is 0.23. But I want to be careful, the bias was actually in my naive regression. So what was the actual bias? It was forcing it to be lower, so it's 0.23, but negative 0.23. I was making that coefficient even larger negative value. Is that any questions on that? Okay with that? Okay. So what I said was that bias should be whatever that coefficient was on SAT when I included it, but I also had in that bias equation the covariance between the variable I included in my naive regression and that omitted variable. So I'm going to look at the covariance here. And I see, okay, athlete SAT score, that covariance is negative 5.4. So I know that the covariance is negative. I actually ran the regression with SAT in it, and that coefficient was what? Positive or negative? I'll get through more things if you answer my easy questions. Positive, right? So this is also going to apply when we start to review things for the exam. So what did I have? I had a positive value here. Variances will always be positive, my covariance was negative. So the bias should be what? Positive times a negative divided by a positive. Sure enough, we found it was negative 0.23. Right? Now, what I could actually do is plug in those values. So without seeing this on the screen, this was like what, 0.0019. I think it was something about that. And we said this was like negative 5.4 something. Now, the only other thing I would need is my variance, right? But if I look at that covariance matrix, it tells me the covariance, but what do the diagonals represent? Well, what's the covariance of a variable with itself? That's simply the variance, right? So I can look at the variance of my athlete variable was 0.04. Right? So all I'm doing there, I then have 0.04, and now I can calculate what the sign of that bias is. So if I didn't give you data, so I think one of the problems in the problem set, I don't give you the actual variable. I think it was like birth order, right? But I give you information that you can identify the covariance of the omitted variable. I tell you what the slope coefficient was if you did include it, and you can identify the variance. You should be able to tell me the bias without simply comparing the naive regression to when you included the variable. Right? So that'll be a question that definitely pops up on the exam, right? Being able to do something like that, okay? So here, so like I would like blank this out, right? So you can't actually see what the new coefficient was using the covariance and the variance and the new, or kind of what the coefficient, if I told you what the coefficient was, you can kind of back out what that bias was, okay? And that's kind of have the math here. If we plug all those values in, sure enough, we get that negative 0.23, which was the bias we saw just simply comparing the coefficients, okay? So it supports that bias equation. I'm not just making it up, okay? Any other questions before we keep moving here? And then this is, I could simply kind of look at what's another way of calculating that bias. So we said, what did that coefficient. I'll use what I wrote down to make the point. What did we say this part of the bias was? It's kind of weird. We'd have to go back a ways. But we said if I take the covariance between two variables and divide it by the variance of one of them, that would be my coefficient from a simple naive regression athlete on SAT. So if I try to predict SAT using, leave myself more room because I forgot the coefficient. I tried to predict SAT, the omitted variable, using the variable I included. This coefficient was just the covariance of those two variables divided by the variance of that X variable I included. Well, I can run that regression in Stata. And then instead of having the covariance and the variance, I have that one single value I can plug in. Now, that value should hopefully be negative 5.4 over 0.04, whatever number that works out to be. We can see if that's actually the case, right? So I'm going to go ahead. These were my non-naive regression. But now I'm going to regress that variable I omitted on the variable I included. So if I go ahead and do that, I get that coefficient of negative 122, which was essentially that covariance of athlete and SAT divided by the variance of athlete. That should be the exact same value. You can check me on that. Take 0.54 and divide by 0.04, but that will be negative 122. Well, now to calculate my bias, I've got that fractions value. Just simply multiply that by beta 2, right? Up here, that was the coefficient of the variable I omitted if I had included it. And I get the exact same difference of negative 0.23. Now, there's some rounding errors here. That's why the numbers vary a little bit, right? Because we're kind of rounding these to the third, fourth decimal, but they end up being the exact same value. Okay, so multiple ways of kind of finding that bias, even if I didn't have the full data. And I left some things out in some of this output. Any other questions on this before we keep moving? And so what I'm trying to do in these do files is we work on this in class, but I try to kind of throw in these more detailed comments. So if you're going back after the fact, don't have kind of what we did up here, you should be able to kind of see something that relates to it in that do file. So we talked about the bias. The next thing we had talked about was sometimes with these dummy variables, we can often get perfect multicollinearity. So this was the idea, like if I had all of those conferences when we were looking at the football data, I have to leave one of them out, right? Otherwise, if I know one, right, I know the value of every other variable. I need a base group to compare to. So the most basic example of this is if I had a racial identifier, one where I identified the individual as Black, one as non-Black. As soon as you tell me the value of one of these variables, I automatically know the value of the other. If we have I understand race is, not binary, you can identify, but like if it's coded as a binary, right, then we would have an issue here. So I can go ahead and try to run this. So I create this variable and I try to include both of these. Notice it identifies perfect multicollinearity for me and it picks one of those variables out. Says you can't do that. So Stata is good at like making sure we don't make a really bad mistake there. If we try to, and this I've done many times by simply copying and pasting and not realizing I put a variable in there twice. Well, if I have the same variable in my regression, I'm definitely going to have perfect multicollinearity. It's always the same value. Once again, kicks it out for me. So that's helpful. Now, we haven't talked about imperfect multicollinearity yet, so I'll kind of hold off on that example, right? We'll kind of return to this do file later. But we did talk last class about multiple dummy variables. Okay? So this was my kind of football or basketball revenue. I forget exactly what sport it was, but I had this NCAA revenue. Let me make sure. I don't know if I ran my global path yet. So let me do that. Come down here, and we'll use that NCAA revenue data. It's a little big. Okay, there. Open it up. You can kind of see it behind the scenes there. So I've now got like, all these different variables. I've got total revenue. Now I also have, when we look at this, we haven't really done anything with these types of variables, but anytime I see red, that is what? Notice every time I have red in here, what are these variables? Text, right? So it can identify if it's text, right? The problem is, can I run a regression? If I need values, can I run a regression with a text variable? No, right? But I can convert these into numerical values, right? For example, if I just assign a number that's unique to every conference, well, then I do have a numerical value, right? So what we're going to do here, and I think I had some values that were missing the conference, that's going to screw us up a little bit. So I'm just going to drop those. So I kept if. Now here's where we'll start to use some conditionals. Anytime we use the exclamation point, right? That means not, right? So I want to keep all of the observations if the following statement is true, if I'm not missing a value for this variable, okay? So that's going to limit my data set a little bit, but it gets rid of basically missing values because I can't do anything with those. So we'll go ahead and I run that and it looks like, okay. In fact, here I was just doing that to be careful. There were no missing values, right? So I've gotten rid of them if they existed. Luckily in this data set, they didn't. So some of these things I'm showing you is more of like good practice when you're working with data, right? We can't use those missing value observations. So one command that is kind of helpful when we're looking at different variables to figure out, okay, what exactly is this, like I have this conference variable, what are the different conferences? I might know nothing about collegiate athletics. So if I use this tab command, it'll tell me all the values of this variable. Right? Now, if it's a continuous variable, why might I not want to use this command? I've got a couple thousand observations and I'm looking at something like income. How many different values are there going to be for income? A whole bunch. So I'm going to have all these values. It's not going to be that helpful. But here, okay, it tells me like, all right, there's only 5 schools. We're independent. 52, I say schools, observations, 52 observations from the Big Ten, 27 from the American Athletic. It kind of tells me what different possible values I could see for that variable and how many observations have that value. So I can see here, excuse me, that I've got this text variable. I can create dummy variables from that. So I could go through and say, I want to create a dummy variable for the American Athletic Conference. I want it to be equal to, now, anytime you put parentheses, right, and you're creating a variable, it generates a dummy variable 1 if this statement is true and a 0 if it's not. So what I'm saying here is if that conference variable is equal to, we have to use double equal signs when we're using conditional statements in Stata, right? But if it's equal to, now here it's not a value, it's a string of text. So anytime I'm identifying a string of text, I have to put quotation marks around it, right? That lets Stata know treat this as a word, right? I think what it actually does behind the scenes, it's like it's alphanumeric. I don't know enough about like computer program, like the actual like stuff behind the computer, but I said essentially that's what it's doing. So every time that the conference is American Athletic, it puts a 1 in for this dummy variable. Every time it's not, it puts a 0. So I can create a dummy variable for every single conference, right? I could do that for the Big Ten, AAC. I could go through and do this for every single conference. And notice every time I've got, where is one of these conferences? Come down here. So anytime I have the Big Ten, my Big Ten variable was a 1, right? Every time I didn't have a conference that was the Big Ten, I can get this here, select these. I've got, these are not the Big Ten, this variable becomes a 0. And then the same thing for the AAC, right, or American Athletic Conference. Every time I had an observation where that variable is equal to that, I have a 1. Every time not, it's a 0. Now, what's going to be the problem with this? If I've got 12 conferences, I can type this out. It's going to take me a while, right? Now, I can do this, right? But there's a much more simplistic way of doing this in Stata. I'll show you one way that's a little bit more tricky, a little way that's going to be easier. So I'm going to drop those variables because I'm going to recreate them doing something else. So I just dropped those variables I created. Here I've got kind of a loop. So how many of you do like a computer programming in any class or anything like that? Not many of you, right? So a loop just says, go through every single one of these things that I'm telling you and do the next line of code for every single one. So it saves me a lot of like typing, right? Now, I'm not going to expect you to kind of do looping in this class, right? But I'm showing you the capabilities of Stata along the way. So here I say, okay, take this new variable and for this whole group of tech, like for the AAC, Big Ten, Big 12, all these different possible words or conferences, create a variable AAC, where it's a dummy variable of the conference name. And here I had to use the abbreviation. So there was a conference name variable, and then there was a conference abbreviation. I chose the abbreviation because the names were shorter, right? But it'll do a 1 if the conference abbreviation is equal to AAC, 0 if not. It then goes to the next one. Create a variable equal to Big Ten if the conference abbreviation is Big Ten. 1 if it is, 0 if not. Goes through this whole list. So that's going to save me a lot of time, right? So I'm going to run this loop. And what I'll see now is at the end of my data set, based off of the conference abbreviation, I've got all these different dummy variables that it created. That saved me a lot of time typing. Now, the problem is, like, I can run this regression, and this is like a pretty naive regression. I just want to know what is total revenue. And I included a dummy variable for every conference, but I had to do what? Leave out one to avoid perfect multilinearity. Now, I probably was lazy here. Yep, I know myself too well. I just copy and pasted the whole list because I knew Stata was going to do what? Identify perfect multilinearity and throw one of them out for me. Okay. Now, if I really cared about having a specific base group, I would have to leave out that group. Okay. So I could run this regression. We talked already last class about I could use this then think about what conference has the highest predicted revenues would be whatever conference has the highest coefficient, which would have the lowest, whichever conference has the largest negative coefficient. So I might ask you to do something almost identical to this on that third problem set, okay? Just not with this data set, okay? Now, I told you that I'm not going to require you to do loops, right? So how could I ask you to do this on the third problem set? I'm going to show you a much easier way of doing this. So if I have a variable and it's text, there's a nice command that should work in Stata where it's simply idot. So idot will take a variable, and for every single possible value, it creates a dummy variable for that and throws them in my regression. So for every conference abbreviation, it'll basically do what my loop did, create an AAC dummy variable, create a Big 10, create an SEC dummy variable, and then put them into my regression. Okay? Now, the problem is if I try to run this, it can't do it. Why? It lets me know it's a string variable, or it's numeric, or it's non-numeric, right? It's a text, okay? I have a way that I can very easily change a text variable to numeric. So I said before, even though it's text, what could I do? I could just make the Big 10 1, make SEC 2. I could make, I don't know, Mountain West 3, right? And assign a value to every single conference. Now I would have a numeric value. So the way that you can do that is using this encode command. So encode will take text variables, make them numeric, and now allows us to actually use them in our regressions, right? So I'm going to use the command encode that says take whatever the original variable is, and then I want to encode it, essentially take a text variable, make it numeric, and create whatever you want to call this new variable. Out of practice, what I usually do is I try to call the variable kind of like the same thing. So here I call it conference, but then on the end I add in REG. What do you think that probably stands for? Regression, right? This is now a variable I can use that was originally text, but I can now use it in my regression, right? You can call it whatever you want. That's just a good kind of good practice, right? Especially if someone else is looking at your code, right? That kind of helps them get the idea. So I'm going to go ahead and run this. It's just creating a new variable based off of a text variable. Okay. So when I'm looking at this now, it looks the same, but what did it change the color to? Blue. A blue variable, it still keeps the text, but the actual value stored behind the scenes, see when I click on it, AAC is stored as a 1. If I go down and click on the Mountain West, it's stored as a, it's kind of hard for you guys probably to see, but a 7. If you're having the data set open along with me, you can kind of see it's putting different values for every conference. Now, every time it's the AAC, it's always a 1. Every time it's the Mountain West, it's always a 7. So I now have this new variable that I can actually use in my regression. So now I can use this really friendly shortcut. I can run the regression where I want to predict total revenue based off the conference by simply using IDOT. What IDOT will now do is for every unique value for that variable, it creates a dummy variable. And the nice thing about doing it this way, like, so I run this, I don't know, it's going to be hard for me to remember that 7 is the Mountain West, 3 is AAC. Well, notice, what does the regression output do? It uses that numerical value, but it still has the name attached to it, right? So it's a lot better for like visual displays if you're going to presenting your results to someone. So it looks no different, right, than if I were to use the text variable, but it can actually use the variable because it's stored as numeric, okay? We hopefully start to see how this might be beneficial. Like, let's say I wanted to predict something about student performance across every university in the country. Well, as long as I encode, like if it comes in and it's the name of the university, all I have to do is encode it, put IDOT, and what can I do in all of my regressions now trying to predict GPA across different universities? I can hold constant what university, like let's say I want to know the relationship between GPAs and your incoming SAT score. Well, now the thought experiment can be 2 students, but I can hold constant the university they're going to. So 2 students going to the same university, but one of them has a slightly higher SAT score. What do I predict the change in their GPA is? That's a lot more powerful of a statement, right? Because there's all kinds, right? IB Tech is going to be in the data set. Comparing them to IU, that's going to be a very different kind of student. So this becomes really, really a powerful command, right? Using this IDOT command. Any questions about this before we keep moving? I think I've said up to this point. Okay with this? All right. So what do I want to think about? We kind of looked at these results for traffic tickets last class. So I had an additional example with limited variable bias. I think might be kind of helpful for us to kind of work through. Let's say I've got, I don't know, I want to try to predict whether or not someone is issued a ticket and if the officer is male. So I'm now using this different data set. So I'm going to open up that traffic stop data. We did a lot of this last class. I think I shouldn't need to run anything here. We just want to go to that additional omitted variable bias, right? This was a lot of the code I used to kind of show you the results I did in last class's slides. So I'm going to run this regression. Oh, what did I not do? I got to create my ticket variable, don't I? Somewhere up here. Here we go. Generate this ticket variable, right? So if the result of the stop was a ticket, it was coded as a 2. I did the kind of hard work to look through not the hard work, but I looked up kind of how things were coded so that I knew that's what that made, or what that represented, sorry. So I'm now going to run this regression. Now it should hopefully run. Sure enough, okay, it looks like from my naive regression that if the officer was male, is the individual more or less likely to receive a ticket? A negative coefficient, the dummy variable, 1 if the officer is identified as male, 0 if not. So how would I interpret that coefficient?
Less likely.
So less likely, but how do I interpret the coefficient on a dummy variable? If the observation has a 1, right, relative to the 0 group. So if the officer is male, relative to not, it's a decrease in what? Well, if my ticket variable is also a dummy variable, changes in my dependent y variable will be changes in the probability. So if the officer is male, the probability that a ticket is issued goes down by 0.03, or as a percentage, 3%. Right? We can kind of go back and forth between probabilities and percentages by simply multiplying by 100. Any questions on that? What levels is it statistically significant at? The p-value is 0. I can reject at every level. A p-value is less than 0.01, 0.05, and 0.1. Every single one of our kind of benchmark values. Right? So if I'm thinking through this, let's say I've got my officer's years of service. Okay. So I ran this very naive regression. So I'm trying to get us some practice with the omitted variable problems because I know that they're going to pop up on the quiz and also the exam. So I was trying to predict whether or not a ticket was issued simply from, and actually, did I say officer male? I forget what it was now. I might have been saying that wrong. What variable did I actually use? Yeah, I used officer male. Okay. I was making sure I didn't have the driver, right? So I simply included, was the officer male or not? Right? So my coefficient, if I have, talking and writing, if I have an omitted variable, right, it's going to give me the true coefficient, but plus this bias, right, from my omitted variable. So the variable I was thinking about was, what if I had included kind of years of service here? So my bias would be what the effect of that omitted variable would have been if I included it, multiplied by what? What was in my numerator? The covariance, right? Between the variable I included, so kind of officer being male, and the variable I omitted that I think is important. And then we said it would be divided by, excuse me, this is where it's a little harder to remember, but it's always going to be divided by the variance of whatever variable you did include. So here it would be kind of officer male. So if I'm thinking through just putting a sign to this bias, well, first of all, what's the variance of any variable? Positive. If I'm looking at this data set, it's a little bit older. So I think this came from like 70s, 80s, and 90s. So what do you think the relationship between the police officers being male and the years of service was during that time? Yeah, I mean, to go back to like the 80s, it doesn't seem like it's that crazy. It wasn't like the 50s, but there was also still like more discrimination against females being in these positions. And so it was just less likely they'd been on the job longer, right? So officer being male in years of service likely has a positive correlation. Without even looking at the data, we can sometimes intuitively think through what our bias would be. What would the covariance be between I just explained the covariance. What would the effect of years of service be on whether or not they issued a ticket if I did include it? Well, that one I'm not really sure, right? I can think of stories that could go both ways. right? The longer you're on the job as a police officer, you just start writing everybody a ticket, right? Or maybe you can identify like who is actually like a danger to society with this vehicle versus not. And so maybe it's negative. So this is going to be an example where it's kind of hard to say sometimes, right? I'd have to be, I'd have to give you, if I was asking you like a problem like this, I'd have to tell you something about what you would expect that sign to be, right? Or give you an example where it was very obvious, or at least ask you to describe to me what you believe. And as long as you tell me what you think the sign is, then I would score it accordingly, right? So my imagination is, I think that, and we'll see if I'm right, I can't remember what the data says, but the longer an officer's on the job, I'm going to just imagine they stop writing tickets as often. I don't know. I just know a couple cops, and I think they become kind of apathetic, and young guns trying to prove something start like writing everyone a ticket. But that's maybe my own bias, right? So if I had this be the case, I would have like negative times a positive, or I think the bias is negative. We can see if I'm right. I might be wrong, right? So if I'm looking at the actual data, right, the easiest way is if I actually had the data, well, I can simply run the regression where I include officers' years of service. There we go. Now you can both see it. So if I do that, from my naive regression, I had negative 0.03. Now that I'm controlling for officers' years of service, what did my coefficient go to? Negative 0.001. So my coefficient estimate actually went down because I eliminated the bias that existed. So in my naive regression, what must the sign of the bias have been? So if this is the actual true effect, this was the true effect plus the bias. This was a larger negative value. The bias must have been. So if I start out, right, this was my coefficient that had the true value plus the bias. That's negative 0.03. Once I include that omitted variable, I've eliminated that bias. So the actual effect should have been negative 0.001. So what must have that bias have been? How would I go from negative 0.001 to negative 0.03? I would have to add in a negative value. So that bias must have been, like I said, subtract this. It's actually going to be closer to what? Negative 0.033 if I want to go out to that third decimal, right? So the bias exists when you run the regression without this important omitted variable. You eliminate that bias when you include it into your regression. So if I'm getting a smaller negative value, that must have meant the bias was negative. Any questions on that idea? It's a little bit kind of tricky there. And you could go through and find the actual values doing like the covariance matrix like we did in my earlier example. I'm not going to kind of take time during class to do that today, but you could kind of work through this and have an additional one. Another thing I had thought about, because I really would like to give you an example where it does the opposite to show you those are actually a little bit easier. So let's see if I can think of one off the top of my head. Let's do ticket. What variables are in this data set? Might not have, we could do aid. So let's say I do the same thing, but I look at driver age, and let's do officers' years of service. Let's see if I get. We're going to have an issue with this regression, which we'll talk about here in a second. But for now, we'll just see if I can get something where I give you an example that has the exact opposite impacts, because I can see some puzzled looks. So let's say I run this. Oh, the variable officers' years, SRV. There's no R, right? Let's try this one. So different value. We'll kind of talk through this, right? So my naive regression, it looks like the driver's age has what impact on the probability a ticket is issued? Just barely positive, right? Now, notice it's still positive when I include that omitted variable, but it's going to be larger, right? So maybe it's easier to work with non-negative values here. So if my bias exists in the naive regression where I've omitted years of service, once I include years of service, my actual coefficient is higher. So what must the bias have been? So maybe writing this down will kind of help. Okay.
On a document.
So when I run the naive regression, this is what I see. When I include that important omitted variable, coefficient estimate I get is the actual estimate. So I was seeing 0.002 once I included that omitted variable. I've eliminated the bias. So if I know the true effect is 0.002, what must that bias have been? If it was positive, I would have actually seen a larger value. So it must have been that this bias was negative. So maybe writing this out like this will kind of help you be able to determine like what that size, or sorry, what the sign of the bias actually was, right? When we're just talking about it, sometimes it can kind of tricky, right? But writing it down, hopefully you can see here, okay, oh yeah, when I include the omitted variable, I'm getting the actual beta 1. My naive regression had the actual beta 1 plus the bias. So that kind of helps me see what that difference was. The difference is simply my bias. Any questions on, yeah. Okay. All right. So we haven't talked about imperfect multicollinearity yet. Where are we at the time? All right. So I want to do today. I know that I want to do this next week where we're talking more about this. So let's go back, switch viewers. I'm going to go back to this regression file. So it might seem like we're doing something unrelated. I'm kind of going back a little bit. And we likely won't get there today. So I said we'll do joint significance on Tuesday. We're likely probably also going to spill over to thinking a little bit more about the R squared and the adjusted R squared again. We talked about it Tuesday, but actually seeing it in Stata, we'll probably wait until do that on Tuesday now. But if we go back to this regression in class F25 that I kind of had up there file, I've got my global path. I'm going to hit here real quick and all the way kind of towards the bottom. So if you scroll down quite a ways, you'll kind of see these like program defined stuff going on down here. So I'm going to go to this first one. And what I'm going to do is I'm going to use this COVID County data set that we had used a couple of weeks ago. And I told you that when we take higher sample sizes, what's happening to the distribution of our sample coefficients? So remember, when we run a regression, we're doing it using sample data. Okay? So if I have a bunch of different samples, I'm going to get slightly different estimates for that slope coefficient. Okay. Now they should be, as long as I have a sample size over 30, normally distributed, and they should be normally distributed around whatever the true population coefficient value is. But now from some samples, I'm going to see some that are a little bit higher, some are going to be a little bit lower, but on average, I should see whatever that true population coefficient value is. Well, I can kind of cheat a little bit here in Stata, because if I have population data, I have a way of showing you if I was to take 1,000 different samples, that this will be the distribution of the coefficients we see. In the real world, like I'd have to go out and get 1,000 different data sets. Like that's not very real of the same exact variables. That's not as realistic. Okay. Now I said, if this was, for example, just making sure that central limit theorem was met, we had a sample size of 30 or higher. What happens if I have more data? Should my estimates be more or less accurate? The intuitive result, more accurate. We said, as I have a higher sample size, what's happening to this distribution? It becomes more peaked or narrow, so that it's guaranteeing I'm more likely to see values that are closer to what that true value is. Okay. So let's see if I can reproduce this for us here in Stata and help solidify these ideas. Okay. Also said differently, just before we do that, if I see the same coefficient from my data set, if I have a higher sample size, what does that do to the statistical significance? Well, before my p-value would be this area times 2. Afterwards, seeing the same coefficient value, my p-value is only the area under this curve. So it should, my p-value is lower, do what to my statistical significance? Increase it or make it more likely I can reject the null that this value is equal to 0. Okay. So let's see if that's the case. Okay. So, excuse me. I had this regression up here. Put it down here because I'm going to have to actually, no, this is a pain. So let me copy this. I'm going to open up that COVID county data and just run this regression where I'm looking at, I'm trying to predict the cases per 1,000 people based off of the percent of the county that was vaccinated. So this is population data. This was every county in America. So this is the true effect. I had every single county. I got the population data. I know this is what my slope coefficient should be. What is it? Negative 0.25. Right? For every 1% increase in the county that was vaccinated, number of COVID cases per 1,000 people, it goes down by what? 1/4 of a person. So, you know, statistically significant, economically, I don't know how significant that is, right? If my whole county is vaccinated, how many fewer people would get COVID? This is the effect of a 1 unit increase. How do I scale up my coefficients? If this is always the effect of a 1 unit increase and I want it, there's a 1%, right? That's how we measured it. How would I get the effect of 100% of my county being vaccinated? Simply take that and multiply it by 100. What if I wanted to know if I had 50% of my county vaccinated? Take the effect of a 1 unit change and multiply it by 50. We can always scale this up to not just be 1 unit, but whatever units we're interested in. At least for now. After the midterm, we'll start to talk about it's not always a linear effect, right? We'll start to talk about non-linearities, but for now, we're treating everything as a linear effect. So I don't know, if I had 100% of my county vaccinated, that would be what? 25 fewer people out of 1,000? I don't know. It's kind of, you know, it's pretty large, but not crazy, right? When I think about economic significance. So let's move on. I would not expect you to ever be able to do this in this class, right? It is creating programs. Once again, I will sometimes sprinkle things in to show you the capabilities of Stata, but only not because I'm like trying to show off. There's people who are way better at writing Stata code than I am. That's why they're doing crazy research projects, right? I'm just showing you the capabilities of it to connect it with some of the principles we're talking about in this class, okay? So I created this program, and what it does is it opens the COVID county data, like uses, we've done that before. Here's this thing where it randomly samples 30 of the observations. It's then going to take those 30 observations and run that exact same regression that I was just looking at for the population data. So it's essentially running the regression, but with a smaller sample. It's then going to store that coefficient, whatever the slope coefficient was, and then go back and do this again. Now, this next line of code says, use this program, which I called coefficient estimate, right? And basically do it 1,000 times, okay? So run this regression, like take a random sample of 30, run the regression, put this coefficient in a new data set. Go back to the data, randomly sample a different 30, run the regression, put that coefficient in the data set. Go back to the data, randomly sample 30, run the regression, put that one. And it's going to do that 1,000 times and create a data set where I now have 1,000 different coefficient estimates, right, from different random samples. So if I do this and I summarize that new data set with 1,000 different sample coefficients, what should they be centered around? Whatever the true coefficient was from the population data, which I was sampling from. So hopefully when I have this 1,000, this set of 1,000 different slope coefficients, if I'm not lying to you, they should be centered right around negative 0.25. Okay, do you have a question?
Yeah, would it repeat, like you said 30 random samples, but if it did it like once again, could it also grab one of those 30 for the new 30 sample?
So you could have the same observation, right? Because it's random, right? So if I randomly sample from 100 people, right, I'm bound to get in every sample I do some of the same people in some of them. but each sample is completely random. So the way that it does this, once again, people who know more about like the actual like computer tech side of the program, it like has these seed numbers, and then like from there it creates random numbers, but it consistently updates the seed so that you're constantly starting with a different value to guarantee that you are truly having like a completely random set of numbers, right? And the random set of numbers is just allowing you to identify completely random observations. So the random numbers would coincide with numbered observations in our data set, right? Like here would be number 20. Here would be 85, but it's randomly sampling every single time. Yep. Okay, so let's run this, right? So I'm going to clear the programs out. I'm going to summarize them when I'm done. So it takes a little bit of time to run. I might have to change this. I think these computers are good, but like 1,000 is a lot. So you notice it kind of takes a while to run here. Okay, not too bad. Okay, sure enough, what is the mean of these 1,000 different random sample coefficients? Really close to that negative 0.25 that I was getting from the population data. Now it's a little bit off, right? Out to like the third decimal, it's not quite right. What would I technically need to get that exact value? An infinite number of random samples? I can't do that, right? Like, but I can get pretty close, right? Now, what should also be happening, right? If I take a sample size of 30, what should be true about the variation in those sample coefficients compared to if I instead randomly sample 100? I should still end up with the exact same mean, right? It's still centered around that true value, but with a higher sample size, the variance should go down, right? I should get a more peaked distribution. So if I do this again, but I do random samples instead of size 30 of 100, what should be true about that standard deviation value I see? It should be lower, right? I should have a tighter distribution on these slope coefficients. So I can also show you the distribution. It's not like truly continuous. There we go. But it's pretty close to a nice normal distribution, right? I mean, it's a little bit off here and there, but once again, it's creating these bins, so there always has to be a cutoff. So if I had a more continuous kind of, or more narrower bins, it would look even more like a nice smooth normal distribution, but pretty close even at a sample size of 1,000, or I should say sample size. The number of samples of 1,000. Okay. So I'm going to do the exact same thing, but now instead of randomly sampling 30, I'm going to sample 100. Right? So I'm going to run this program again. I'm going to summarize these coefficients and then show you the distribution. Now, before, just one way of showing this, the distribution, we saw some of the sample coefficients were as low as -1. Some of them were as high as like just above 0.5. When we run the new program where it's 100 as our sample size, what should be true? If the distribution becomes more peaked, these values on the edges should be less likely for us to see, or we shouldn't see as extreme values on the left and right-hand side. So we'll see if that's true, right? So I'm going to run this program where I'm now randomly sampling 100 people. Now, if I do this, we said we should still have the same mean. That should still be centered around that true population value of -0.25. It should be that our distribution is a little bit tighter. Well, before, we were seeing values as low as -1. Now we're only seeing values as low as -0.6. We were seeing values as high as 0.5, now only 0.2. So it looks like our distribution is narrower. But what's one statistic we can use to actually see if it was? That standard deviation. Before, our standard deviation was 0.23. Now it's only 0.12. So we can kind of prove to ourselves that these things we're saying about that slope coefficient are in fact true. Now in practice, we don't have 1,000 samples, we only have one, right? But we know that if that sample is of a higher sample size, it's always going to do what? Make that distribution more peaked. So seeing the exact same value should decrease our p-value and make it more likely we can reject. And in fact, that higher sample size even seeing the same slope coefficient, why was it making that p-value smaller? What was it actually impacting? So if we go back, and we'll see questions like this on, like I said, the practice exam. How do I calculate a test statistic for a slope coefficient? It's that slope coefficient divided by what?
Standard error.
Standard error. With part of our standard error equation, we had this thing in the numerator, but it had n-1 in the denominator. So when we were taking higher sample sizes, what was that doing to this fraction? Higher denominator would make the fraction smaller. I would do this when it asked questions like this. Don't try to think through it in your brain. Write down a fraction so and arrows, and it's very easy to see. When my denominator is larger, this fraction is smaller. So this fraction represents, if I had the actual equation for my formula sheet, would be my standard error. So if my standard error is lower, seeing the same coefficient, what's happening to my test statistic? It's getting denominator smaller, test statistic is larger. If I'm looking at a distribution, the further out I go, the further out this test statistic is, the area to the right of it is going to be smaller. That area to the right of it really represented half my p-value. So it's getting smaller, which if my p-value is smaller, am I more or less likely to reject the null? It's more likely my p-value is going to be less than alpha. So that we can kind of prove to ourselves with data, but this is like kind of more of the like theoretical side of it. So I wanted to go back and revisit that because a very similar thing will start to happen when we talk about the R squared. So I thought it was a good time to kind of go back and revisit this as we're getting closer to the exam, since we'll start to see kind of questions like this as we start to prepare for it. All right, any other questions about this kind of exercise before we keep moving? Just hopefully, does it look familiar at least? I know it's going back a little bit, but we got to start to kind of think about doing some review of this old stuff. So I want to go to in-class practice quiz for today. And I want to kind of take a look at these questions. I think just given the time where we're at, I'll kind of run through a few of them. I think we'll hold off on imperfect multicollinearity until Tuesday. So I kind of lied to you at the beginning of class. There will be a part of that problem set 3 where it talks about imperfect multicollinearity. So there will be one other question that we'll kind of have to wait on that third problem set to answer until after Tuesday's class. But we'll talk through the theoretical side of it as well as stata in Tuesday's class. So start working on that problem set 3 early, and that way these two and a half questions that we can't quite get to until after next Tuesday's class, well, next Tuesday, the Tuesday after this weekend's class, then you can kind of finish up on those next week. So let's look at some of these problems, right? So let's say I had this first one, and you'll notice I'm really hammering this sign of the bias stuff, right? So that probably means that it's going to show up, right? And when we're looking at the quiz this week, the third quiz is also the exam. So I've got kind of college GPA and whether or not I work a job. So working a job is just a 1. If the student works a job while in college, 0 if not. College GPA is your college GPA. Yeah, this is published. It should be, it's not assigned, this isn't an actual in-class quiz. This is just practice questions I want to work through. So you'll kind of notice I should be down here. That practice in-class quiz, number 3. So I just kind of, I can call them something different if it helps. I don't know. Maybe I'll change them to be practice problems because they're not, there's practice, so they're not for points. Maybe I'll do that after class just to make it obvious. But we're just kind of thinking about, these are the types of questions I could use in an in-class quiz, could use on a quiz, could use on an exam. So just additional review for you guys. So if I've got this, right, I should be thinking about, when I'm running this regression of GPA in college, all I've done is kind of include this job of whether or not, or job, dummy variable of whether or not they're working a job. So the coefficient estimate I see will include the true effect plus this bias component, right? But the bias between what? So I think in this example, I said, what if I left out an important variable, which was parental income? So this is one where I'm giving you something where I think the sign is obvious, right? So the variable that we omitted was parental income. So I didn't include this in my regression. But if I did, so now I'm looking at, okay, what was the omitted variable? It was parental income. So I want to look at the covariance between the variable I included, and that was also the variance in my denominator, and then parental income. Okay. So if I'm trying to put a sign to my bias, what do you think the effect of parental income would be if I had included it into my regression and trying to predict GPAs? Now, I'm not for sure on this, but my guess would be typically income is correlated with what? Why are all of you here? You're getting an education because you want to make more. Yeah. Yes. So I would imagine parental income is likely a huge factor that's correlated with would be education levels. So if my parents have a higher education level, that likely, all else equal, means maybe they had higher IQs, higher intellectual ability. If genes are in any way passed down, what would you think that correlation then would be between parental income and GPA? Positive, right? Now, you could argue, I don't know, your parents are wealthier, you pick up bad habits that make you not, because you've coasted through life. And so now you don't study as hard. So you could tell me a story where you think that is negative. But for us, let's just think about it being positive. Well, this one's easier to me. If your parents have more income, is it more or less likely you're working a job in college? Less likely. I don't know all of your friend groups. When I was in college, everyone's parents who were wealthy did not work a job, right? And so I would imagine this is going to be a negative covariance. Now, variances are always positive. So what's the sign of my bias likely going to be? Positive times a negative, probably negative. So when I run this naive regression, it's going to look like working a job while in college actually has a negative impact on your GPA. But possibly it's just picking up a lot of that negative correlation between this important omitted variable that you left out. Right? I think if you include enough controls, often these data sets, where I think the one we looked at with GPA, there is a working variable. It actually often tends to be positive, which always blows my mind because you have less time to put towards things. But usually it's working a job. You have to be better at time management. So you don't sleep through a class, right? Or you don't ill prepared for an exam or things like that. So we could see a completely incorrect sign, right? If this negative bias was large enough, maybe the true effect, sorry, I wrote a hat above that. This is going to be the true effect. Maybe this is something like, I don't know, it's a positive value, right? GPA probably makes sense if it's something like 0.3. But when I had the negative bias in there, maybe for my regression results, it only looks like working a job. It could actually flip technically the sign, right? If this bias was negative 0.5, the true effect could actually be positive. But when I omit this important variable, the result I see actually is negative, right? So a lot of the examples we looked at today, the sign of our coefficient was still the same from our naive regression when we omitted a variable, when we included it. But if the size of the bias was large enough, it could actually flip the sign of the coefficient we see compared to what the true effect actually is. So any questions on this before we kind of go back here? Okay. So this one's also going back a little bit, right? But if we think about if we had hetero versus homoscedastic errors, this is some old stuff, but I wanted to kind of starting to do a little bit of review at the end of these classes. If I have errors that are in fact heteroscedastic, we always start out, right? Our very general basic regressions treat them as though they're homoscedastic, right? We had to add in what command in stata to make it treat it heteroscedastic. Do you remember? R, O, B, U, S, robust, right? So we added in this command of robust at the end, which made it treat the errors as heteroscedastic. So if we don't add this in, or we don't treat the errors as heteroscedastic, we said our homoscedastic errors are actually going to be what, right? So our standard errors, if we incorrectly treat them as homoscedastic, right, are actually going to be lower than what they should be. So when we're thinking through this, right, my test statistic will be whatever that slope coefficient is over my standard errors. If I treat these errors as homoscedastic instead of heteroscedastic, so I incorrectly treat errors as homoscedastic, my standard errors that I see are actually going to be smaller than what they should be. Hopefully when we get to the end, you'll see like it's easier to connect like beginning to the end, the parts in between. Maybe this isn't very like obvious why yet, but I think once we get to the end, that intuitive result will connect. So if I've incorrectly treated these errors as homoscedastic, there's actually more variation in them. Well, more variation would mean that my standard deviations or my standard errors would actually should be higher. So if I don't correctly treat them as heteroscedastic, my standard errors will actually be too low. If my standard errors are lower, incorrectly treating my errors as homoscedastic, what's going to be true about my test statistic? It's going to be higher. If my test statistic is higher than what it should be, what's that going to do to the area to the right of it? Make it smaller. What does the area to the right multiplied by 2 represent? For our linear regressions, we're always using a two-tailed test, so that was our p-value. So if the area is smaller, our p-value is going to be lower. If our p-value is lower, are we more or less likely to reject the null? So when we incorrectly treat those errors as homoscedastic, we're more likely to find statistical significance, right? Once we use that robust command and control for the fact that these are heteroscedastic errors, everything would go in reverse, right? Our standard errors are actually higher. Our test statistic will end up being a little bit lower. Our p-value will end up being a little bit higher. And we're actually less likely to reject the null if we've treated them correctly like they are heteroscedastic errors, okay? So going back to these things and kind of thinking about how, with our test statistic, how changes in that standard error kind of impact whether or not we can reject them. And it kind of makes sense. Like if there's heteroscedasticity, there's more variation than what we're accounting for. It's gonna make it, right? We're treating it like there's less variation. It's gonna be more likely we can reject the null. So it's again, kind of revisiting some old topics just so we start to sprinkle these in as we get closer to that exam, okay? All right, so I'm kind of running out of time here. But I had kind of another question in here, which was talking about slope coefficient estimates. We've got some kind of R-squared stuff that we'll talk more about on Tuesday's class. We also spent a pretty good amount of time working through the state example where I talked about statistical significance of our sample coefficients based off of like the sample size. So some of that is what I wanted to kind of get at with this question. So we'll revisit this. I might pull this in practice quiz, or I'll change it to practice problems or in-class practice problems. We'll kind of revisit this third question after Tuesday, during Tuesday's class as well. So I will kind of have posted after class, kind of ready to go, is that third quiz.
Yeah.
Okay. So that'll be due. I've got it set currently to be November 9th at the end of the day. That's next Thursday. So you'll have a week. I've had those practice problems up there. You should have been kind of reviewing them. It'll be everything that we've covered up through kind of today's class, right? So that quiz will be due by the end of next Thursday. So you've got a week to do that. That problem set will be due the following Tuesday. I think it's the 12th or whatever it was, whatever that Tuesday is before we have the exam, I believe is the 16th. Any questions as you're kind of working through these materials? Gave my B251 exams last week. My office hours have been kind of nuts, but next week, kind of moving forward, office hours should be pretty open. So if you want to come ask questions as we're getting closer to that midterm exam, we're working on that third problem set. That will be a good time to do it. Okay. All right. Fun, safe weekend, and I will see you guys on Tuesday.